So topic 2.3, we're going to start our real proof writing, which I know can be kind of scary. You've probably heard scary things about proofs. But I try to give you guys like patterns to look at. That's part of the reason why we have the vocab sheet, right? I don't want you guys guessing. I want you guys using context clues, looking for patterns, things like that. So a couple things, when we write proofs, there's some proper proof technique to use. Like grammar, you know, like when you're in English class, you can't just write things any old way you want. You got to follow grammatical rules. Same things kind of happen in geometry where we need to follow some geometry rules. Segments and angles, we say that segments and angles are congruent, while length and degree measure are equal. So if I use a little segment bar, right, or my angle symbol, we use our congruent symbol, that's called a congruency statement. But if I'm talking about length or measure, like M of angle A, or just like two letters without the bar above it, those are equal signs, those are equations, because they technically represent numbers. When you use algebra properties, you have to use measurements and an equal sign. Okay, so if I wanted to use the subtraction property of equality, I can only use that if I have an equation. So there has to be an equal sign there. And you can state givens from a picture, but you have to state it. So if you notice something in your picture, you can use it, but you have to say in your proof that you're going to use it. And we'll see an example of that in a second. So a couple new theorems. Now what happens is when you have a theorem, theorems are things that can be proved. They're geometric statements that can be explained or proved or justified. When we did postulates, they're a fact. You accept them, they are what they are. But theorems can be proved. So what we're going to do is I'm going to give you a new theorem, and then we're going to prove it. And then once we prove it, you can use it in the future. You don't ever have to prove it again. But it'll help us kind of like start to formulate like a process for doing this. So our first theorem is called the linear pair theorem, and it says if two angles form a linear pair, then the angles are, and there should be a little line here, I think my picture covered it up, but it should say that they are supplementary. So if two angles form a linear pair, then they are supplementary. And if we look here, if you're like, wait, what's a linear pair? This is a linear pair right here, this diagram. So a linear pair is when you have two angles that are adjacent, so they're going to share a vertex and a side. And see down here how they form opposite rays? That's how you know it's a linear pair. So we're actually going to prove this. We're going to show why this works. That's what a proof is. It's basically a fancy explanation. Okay? So we are given, and do you remember when you did your algebra two-column proofs, you had your given, right? That was your equation, and then your proof, that was your final solution. These are kind of similar. You're going to be given some important information, and then you're going to use that information to end up where you want to end up at. So we're given that angle ABC and BCD are a linear pair. We want to prove that they're supplementary. So we want to prove, basically, what does it mean if two angles are supplementary? What does that mean, Colin? That they add to 180. So we're going to prove that these add to 180, basically. Okay? So what I've done here is I've filled out all our statements. So we're going to go through and look at those. We're just going to figure out our reasons. Now, when you do a proof, your reasons are either definitions, theorems, postulates, or properties. And guess what we all have a sheet of now? All of those, right? So you have all of your possible reasons actually on this vocab sheet. So we're going to use our context clues and kind of look through this. So first thing, angle ACB and BCD are a linear pair. What's your first reason all the time, no matter what? Oh, okay, thank you for letting me know, Daniel. Oh, he's gone. He'll watch the video later, maybe. Okay, what? The given, yeah. First thing is always just given. Okay, good. Now, okay, now it's telling us that ray CA and ray CD are opposite rays. And you're like, okay, great. I can see that in the picture, but like, I need a reason, right? That's so how these work is they're like if-then statements. If your hypothesis, then your conclusion. So like if you look here, if they're a linear pair, then I have opposite rays. The question is why? How would I ever be able to figure that out? Well, if you go to your vocab sheet, there is a definition of linear pairs. And for today, I'll read it to you, but in the future, I might make you read it to me. And it says, it's down kind of towards the bottom of the front. For a linear pair, two angles form a linear pair if and only if they have a common side and non-common sides are opposite rays. So do we notice something in that definition? Linear pairs are formed by what? What's that last word in the definition? Opposite rays. So if we have a linear pair, we know we're going to have opposite rays. Well, how did we know that? What definition did I read to you? Definition of a linear pair. So guess what? That's our reason. Definition of a linear pair. And you can't just write linear pair because there's a linear pair theorem too. You have to put definition. And I abbreviate. I put def. But if you notice something, and I do a lot of highlighting with these. Wasn't I given a linear pair? So then didn't I use the definition of a linear pair? Yeah. See, I was given linear pair, so I used its definition. Well, look at your second step. Do we now have a new vocab word that I highlighted in yellow? Opposite rays. If I look at my vocab sheet, do you think there's a definition of opposite rays? Probably. Let's look. Opposite rays. Two rays are opposite if and only if they have a common endpoint and form a straight angle. Oh, interesting. What does step 3 say? A straight angle. Is it a coincidence? It is not. It is not a coincidence. So we have opposite rays. Opposite rays are going to give us a straight angle. How did we know? The definition of opposite rays. Okay, so if I give you a vocab word, chances are I want you to use it as your reason, okay? Now, why is this? Now, for this, I'm giving you all your statements, right? We're just trying to figure out our justifications, but where are these statements coming from? Well, first of all, we're using our context clues, but aren't we at the end of the day trying to prove things are supplementary? And if they're supplementary, Colin told us they have to add up to be 180. How would a straight angle and things adding up to 180 maybe connect to each other? How would those maybe connect? And people online, you can answer too. Don't leave these poor 3 gentlemen just hanging as I stare at them because there's nowhere else to look. But how could a straight angle and things adding up to 180 maybe connect to each other? I won't look at you. I'll look over here. Anyone at home have an idea how straight angles and 180 could connect? Oh, come on, guys. What makes... Oh, you're overthinking. You're thinking too hard. Think less. Think less, Colin. Yeah. How many degrees is a straight angle? 180. Supplementary is also 180. So could these things connect? I think so. Yeah, Tyler, you're just thinking too hard. Yeah, think less. So that's why it's kind of leading us down this path. So now we have a straight angle. So here's a new vocab word. If I have a vocab word, guess what I'm going to do? Okay, I'm going to highlight it because I like color coding, but what else am I going to do? I'm going to look at my vocab sheet and I'm going to read it to you. We're going to have story time. So a straight angle. An angle is a straight angle if and only if the measure is 180 degrees. Well, look at that. What's your next line say? 180 degrees. What? Crazy. Okay, so guess what? A straight angle, if it's a straight angle, then I know it's going to equal 180 degrees. How did I know? The definition of a straight angle told me so. And I have a tendency to like draw angle symbols instead of like right angle, and that's okay too, but do what you're comfortable with, okay? All right, but now I've run out of vocab. 180 is not a vocab word. Darn. But it made those first 3 lines really nice, right? Okay, so but now I have that the measure of angle ACD equals 180. And then in my next line, it's telling me that the measure of angle ACD equals the measure of angle 1 plus the measure of angle 2. I have a little bit of a problem because if you look at your picture, are either of them labeled as 1 and 2? No, so let's do that first. So I don't care which one you make which. I'm going to make this one angle 1 and that one angle 2. So go ahead and label that. Okay, so in this step, this is one of those steps that's a little disconnected from the step above because I ran out of vocab, right? So I needed to look, what else do I have? Well, I have that angle ACD is 180 degrees, which is great and all. But if you look at your proof, oh, and I guess I forgot I had changed. I made ACD and BCD into 1 and 2 because using all those letters gets confusing. So we can do that in our given too. Make this one angle 1 and make this one angle 2, if that helps you. I tend to use numbers instead of all the letters. But I have that angle ACD is 180, but don't I have to show that angles 1 and 2 are 180? So I need to find a way to introduce them into our proof. They don't magically just like appear. I don't get to just magically at the end say angle 1 and angle 2 have appeared in my proof and they're supplementary. I have to introduce them into my proof. And the way I'm going to introduce them into my proof is that showing that this straight angle is actually made of angle 1 and angle 2. So that's what we do here. The measure of angle 1 plus the measure of angle 2 equals the measure of angle ACD. Because if I take this angle and I smush them together, right, I take my part plus my part, isn't ACD the whole thing? Yeah. And there's a postulate that lets us do that lets us add angles together, and it is called the angle addition postulate. And that step's a little trickier because it doesn't have that pattern going on. Okay, but now I've introduced angle 1 and 2 into my proof, which is good. And now if you look at the next line, angle 1 plus angle 2 originally equaled the measure of angle ACD, but now it magically equals 180. Huh. Well, what changed, right? Look at what changed from one step to the other. It equaled the measure of angle ACD, but now it equals 180. Well, if you look at step 4, didn't ACD equal 180? If things are equivalent, am I allowed to like replace them for each other? Yeah, is there a property that lets you like take a value and replace it with another one, Colin K? It is the substitution property, absolutely. And I promise my handwriting is so much better than it looks on this. It doesn't work out the same. And now guess what? We're on our last step, right? And isn't your last step, I know I don't have a vocab word in this line, but doesn't your last line have a vocab word in it? What vocab word's in your last line? Supplementary. And if you look at your vocab sheet, it says angles are supplementary if and only if the sum of the angles is 180. Well, in the line above, didn't I show that their sum is 180? So can I say they're supplementary now? Absolutely, by the definition of supplementary angles. Oh, wow. Pretend that says supplementary. So now let's talk about our next theorem. And then what do we have on the back? I just want to see, because at some point, the nice perk about us doing this together is at some point we take a little break, because I just don't like talking for that long in a row. And you don't want to listen to me for that long in a row either. So let's look at vertical angle theorem. So this is our next new theorem for today. We've talked about vertical angles some, right? Those are the ones that are formed by your intersecting lines. And our vertical angle theorem says if angles are vertical angles, then they are congruent, which we've mentioned, but now it's just a theorem. It's official. We can use it all the time. Okay, if angles are vertical angles, then they are congruent. So we are going to go ahead and prove this. We are given that angles 1 and 3 are vertical angles. We're going to then prove that they're congruent to each other. And this one I did the opposite. I gave us all the reasons. We're going to now try to figure out our statements. So first thing is always your given. So let's go ahead and fill that in. So angle 1 and angle 3 are vertical angles. Okay. And now it is telling us to use the linear pair theorem. Oh, something else I would do, guys. You actually have 2 freebies. Yeah, you have 2 freebies, your first step, and then your final statement are your freebies. So we know we need to get to angle 1 being congruent to angle 3. So you can always fill that in right away too. Okay. So we got to prove these are congruent. This one's not an easy one either, because proving the theorem tends to be trickier than the ones I actually give you to do. We use things we already recognize, so they're not as hard. But what we're actually going to do here is we're going to use what we just learned. We just learned the linear pair theorem, right? And if you look at this picture, I have some linear pairs. 1 and 2 is a linear pair. 2 and 3 are linear pairs. And I'm going to use that to prove 1 and 2 are congruent. So the linear pair theorem, and that you can either look up at your paper or look at your vocab sheet, it's on both. Linear pair theorem says if 2 angles form a linear pair, then the angles are supplementary. And if you look at your picture, I have some linear pairs. 1 and 2 are linear pairs, 3 and 2 are linear pairs, and if they're linear pairs, I can say they are supplementary. So let's do that. Angle 1 and angle 2 are supplementary. And I have a tendency to abbreviate supplementary because it's just a long word. And then angle 2 and angle 3 are supplementary. Okay. Now, we're in that lovely place where I have a vocab word, don't I? I have the vocab word supplementary. And if you look, isn't it telling me to use the definition of supplementary? So again, you could always look at your vocab sheet. It says angles are supplementary if and only if the sum of the angles is 180 degrees. So guess what I should say about angle 1 and angle 2? They equal 180 degrees. But I'm going to say it in a, since we're going to start using numbers, I'm going to write it as an equation. You don't want to just write, they are 180. You write an equation for it. So I'm going to say that the measure of angle 1 plus the measure of angle 2 equals 180. And I'm going to do the same thing for 2 and 3. The measure of angle 2 plus the measure of angle 3 equals 180. So again, I gave you a vocab word, so we used it. But now we're out of vocab words again. But context clues. Proofs are big on context clues. If you look at these 2 equations, do you notice, don't they equal the same number? Typically, I'm going to tell you in proofs, when 2 things equal the same thing, again, it's not a coincidence. You're going to need to probably do something with that. Now, how would you, if you were doing this on your own, you're like, how in the world am I ever supposed to know that? Well, at the end here, aren't you supposed to show angle 1 is congruent to 3? And if you look right now, aren't 1 and 3 in totally separate equations? We don't want them in separate equations though. We want them in the same equation. We need to show they're congruent. So the best way for me to do that is to combine two equations I have, right? And I can do that because they both equal 180. If they both equal 180, do they equal each other then? And it gives you the hint of our transitive property here. And that's, again, that's in your vocab sheet. The transitive property says if two things equal the same thing, they equal each other. So let's set those equal to each other. So the measure of angle 1 plus the measure of angle 2 equals the measure of angle 2 plus the measure of angle 3. Again, I could say that because these both equal 180. Are you guys with me so far? I know this is a lot for our brains sometimes. Okay, we're almost done though. It's now telling me to use the subtraction property. Oh, I'm back on here. Let's see if I can join again. Awesome. Okay, cool. So it's telling me to use the subtraction property. And if you look, we got this big giant equation, but I don't want all that information. Don't I only want information about angle 1 and angle 3? Colin, you look like you have a thought. Yeah, very good. I have angle 2 in there, but I don't want angle 2 when I'm done, right? And I have it on either side. And if I have something on either side that's being added in, I can subtract it out. So again, we have these on either side. I don't want them there though, because all I want is 1 and 3. So I'm going to use my subtraction property to get rid of them. So I can then say just the measure of angle 1 equals the measure of angle 3. Now, why weren't we done there? Right? You're like, well, right, why do I have one more line? Well, doesn't your proof specifically have a congruent sign? Equal signs and congruent symbols, they're similar, but they're not exactly the same. If there's an equal sign, that's an equation. That's like this number equals this number. Congruent symbols specifically mean it's like more using their labels. So anytime you guys switch from saying two angles are equal to saying they're congruent, just use the definition of congruence. It's technically the definition of congruent angles because if their measures are the same, they're congruent, and vice versa. And you can do that with segments too. Theorems anymore. These are just some regular old proofs. We're going to use definitions. We're going to look at our context clues, and we're going to see if we can figure these out. And you'll notice, I guess this one, no, these ones aren't quite as long as the ones we just did. And some of them, I think on your homework, some of them are just like 3 steps. So it's just like figuring out one definition and how it can help you. So some are really long, some are really short. Well, I tend to give you medium to short ones to do on your own. I think there might be one on your homework that's a little long, but I fill out some stuff for you. And it's like one that I want you to do the best you can. So number 1 says, given that ray BD is an angle bisector of angle ABC and the measure of angle ABD is 80, prove that angle DBC is 80. Now, before we even write anything down, let's just use some logic here, some things we already know. What does an angle bisector do to an angle? Colin? Splits it into 2 congruent angles. Absolutely. So if I have an angle bisector, I'm going to know these guys here are congruent, right? And doesn't it tell you that one of them is 80? Oh, my thing turned off. Doesn't it tell you that one of them is 80? Yes, it does. I know, it's weird. In a room of 3, it's a challenge. Yeah, always. So if one of them's 80, if they're congruent, isn't the other one going to be 80? Okay, so thank you. So we already know, right? If you were just like, if I just asked you this on a homework, you'd be like, yeah, they're both 80. All we have to do, we're going to write it like officially, right? We're going to write it in our nice fancy proof format. So we're going to just follow our steps here. So first thing is always your given. That's your freebie. Put in your freebies. So we know that ray BD is an angle bisector of angle ABC. Again, pardon the terrible handwriting. It's almost impossible to write small on this thing. And the measure of angle ABD equals 80. I'm going ahead and putting them both in one line because I like to get all my givens out of the way. Some like textbooks and some teachers like to put them in as you use them. I like to just put them all in so we can't forget about anything. So that's my given. We are going to prove that the measure of angle DBC equals 80 degrees. So there are my freebies. If you use your freebies, bless you. If you use your freebies, I mean, that's something, right? At least put those in at minimum. So let's use our context clues. Always look and see, was I given a definition, right? What do I know? In your given, were we given a definition? Yeah, what vocab word? Angle bisector, right? Good. I only say specifically because there's also segment bisectors and they're a little different. I know, it's real ugly, I know. So angle bisector. So look at our handy dandy vocab sheet and it says a ray is an angle bisector if and only if it divides an angle into two congruent angles. So if I have an angle bisector, I can say that two of my angles are congruent. So let's say that. Now the question is, which two angles? Well, can we get our names from our picture here? Yes, yes we can. Yes we can. So we are going to say that angle ABD, so angle ABD is congruent to angle DBC. How could I say that? Well, we used our vocab word. So we used the definition of angle bisectors or angle bisector, it doesn't matter, right? But I gave you a vocab word and we used it. So now we're out of vocab words, but we do have a little congruency statement, don't we? But if you look at your, thank you, Colin, loving the enthusiasm. But if you look at the end, do we have a congruent symbol in our last step? We have an equal sign. Very, very similar, but not exactly the same. Now, if things are congruent, are they equal? Yes, and vice versa. So we need to, if we have a congruency symbol, what I'm trying to say is if we have a congruency symbol, but we want to end up with an equal sign, we need to fix that. We need to change it. And if we can say that these two angles are congruent, we can also say that their measures are equal. So what we're going to say next is that but not an highlighter. That would be hard to read. It's already hard enough to read. So the measure of angle ABD equals the measure of angle DBC. So now I have my magical equal sign. But so now the reason is, why can I say that? We knew we needed to do that because we need an equal sign at the last step. But what lets me switch between congruent and equal? Well, if angles are congruent, do they have the same measure? Yes, that's actually one of our definitions. It's the definition of congruent angles. And you can write it that way, or we have a tendency to just abbreviate it as the definition of congruent. So again, anytime you switch from equal to congruent or congruent to equal, we say the definition of congruence. And that's just a really ugly congruent symbol. I'll write it out. Oh, but that didn't do what I wanted it to do. Don't tell me we're going to glitch now. No, we fixed ourselves. Okay. Okay. So anytime you switch between the two. All right. So now we have an equation. It's almost where I want it to be, but not quite. we have angle DBC in there, which is good. We need that at the end, right? But we need to show that angle DBC equals what? 80 degrees. Well, look at your given. Do I know something about angle? Someone just scared me. Do we know something about the measure of angle ABD? Look at your given. We know that it equals 80 degrees. So can I take 80 and substitute it in there? Yes, I can. If I know angle ABD is 80 degrees, then let's take that, let's plug it in, because that's where I needed to go. So we're going to say 80 degrees equals the measure of angle DBC, and we substituted that in. So substitution. Now, why weren't we quite done yet? Well, if you look at your given, or you look at your proof, is the step before that in the correct order? No. But are we allowed to switch our order around? Yeah, anyone remember what property lets us take an equation and switch it in the opposite order? Yeah, symmetric, good. Symmetric. Good. All right. Okay, two more. Two more, and then I'll take a break from talking for a little while. I'm not used to talking this much. We'll see if I have a voice at the end of the week. All right, two more, guys. Here we are given that the measure of AB is 5, the measure of DE is 5, and segment DE is congruent to segment XY. Prove that AB is congruent to XY. So don't look at your don't look at your table yet. Let's just look at the picture. Let's label what we know. We know that the measure of AB is 5, the measure of DE is 5, and we're told that segment DE is congruent to segment XY. So we can put our little congruency marks in there. So this one is congruent to this one. Now let's just think logically for a second. AB and DE are both 5, right? Okay. But wait, DE is congruent to XY. But isn't DE 5? So that means XY is 5. And if XY is 5 and AB is 5, won't those also be congruent? Yes, that's what we're going to do. So we're going to show that since these have the same value, XY will also have the same value, which will then make them congruent. We just got to write it out all pretty now. So let's say that the measure of AB equals, oh no, we're back. Okay. The measure of AB is 5. The measure of DE is 5. And the measure of, I'm sorry, and I don't know where I'm getting any of these numbers from right now. Oh my gosh, why is this doing this to me? There we go. Okay. And the measure of, or I'm sorry, segment DE is congruent to segment XY. We are going to prove that segment AB is congruent to segment XY. Oh, and don't forget to put first step is always given. Okay. So couple things, couple context clues here. We need to, at the end of this proof, have AB and XY together, right? The congruency symbol, our little segments and everything. But take a look in between them. I know AB equals 5, DE equals 5, and XY equals DE. So what we're going to have to do here is show that all of these parts have the same values. So let's just start, let's go in order. Don't I know that AB is 5 and DE is also 5? If they both equal 5, what can I say about them? They're congruent, or since we're using numbers, we'll say they're equal. But yeah, we're going to say that they're equal. So we're going to say that AB equals, well, is that the way I want to go with this? Sorry, I'm thinking real quick. Because I want to make sure I do it like the most straightforward way for you guys. I'm trying to think if that's the most straightforward way. Actually, yes, that would work. Okay, so I'm going to say that AB equals DE. And that's either substitution or transitive, whichever way you want to think about that. Because don't they both equal 5? So they equal each other. Or you can think of it as you're plugging one in for the other. I prefer to say transitive, but that's just me. Okay. So now I have AB is congruent to DE, but don't I need to end up with is equal to, but don't I need a congruent symbol? Am I allowed to switch from equal to congruent? Yeah, we can do that. So let's do that now. Segment AB is congruent to segment DE. And I can say that because of the definition of congruence. I'm allowed to switch. And if you look, I'm actually really close to where I need to be. Don't I have AB on the left and then a congruent symbol? I just need to figure out a way to switch this to an XY. I actually have an extra line here that I don't even need. Colin? You're so close. But yes, it's just not substitution because it's not an equation. It would technically be the transitive property. Because if you look at your given, this time they both have DE in it, right? So what you can do, since they both are congruent to DE, you can take your XY and say that's equal. It's just, again, it looks like substitution. Right, it technically, because substitution only works for equations, and this is a statement of congruency. I would probably, like, if it was a free response problem, I'd probably give it to you because I'd be like, yeah, I see what they're doing. Technically, though, it's the transitive property. And guess what? I had an extra line. We don't need that line because this one, there's more than one way to do it. I did it a longer way last year. So there we go. I made it easier for you. So I can go ahead, and since they're both congruent to DE, then AB is congruent to XY. I know they're congruent to each other by the transitive property. But this is actually a good example, guys. There's normally more than one good way to do these. I'm going to kind of lead you in a certain direction during notes and on tests and stuff. But if you're at the point where you're given a completely blank one, there's maybe more than one good way to do it. Okay. Last one. We'll even get done early. That's nice. Okay, good. I bet there's some people that probably disagree, but that's okay. Steven's looking at me like I'm done. One more, Steven. We're almost there. All right, so here we are given that segment AB is congruent to segment DE, and B is the midpoint of AC, and E is the midpoint of DF. We're going to prove BC is congruent to EF. So first, let's look at our picture and label it. AB is congruent to DE. So mark those as congruent. And I want to show that EF is congruent to BC, right? Let's look at our context clues. We're not going to write anything down yet. We're going to kind of plan what we want to do. Well, are we given some vocab? Midpoint. What's a midpoint do to a segment? Yeah, it splits it in half into two congruent segments. And if you're like, I don't remember that, guess what you should look at? Your vocab sheet. That's why it's here, right? You can use this all the time on everything. Yes, you're welcome. Because there's a lot of vocab. There's a lot. I so rarely make you guys memorize things in this class. I'm more worried that you can do it, you know? Yeah. Okay, so I know if B and E are the midpoints here, it splits them up congruently, right? So I know the left and right-hand sides on either one are going to be congruent. So if I know the left-hand, right-hand sides are going to be congruent, but the left is congruent in both of them, won't the right also be congruent in both of them? Yeah. Okay, so we're going to go through and we'll probably have to do a little substitution or some transitive property or something. You'll see that those things come up a lot. So let's put in our given. Segment AB is congruent to segment DE. And B is the midpoint of segment AC, and E is the midpoint of DF. That is given. All right, and we want to prove that segment BC is congruent to segment EF. So, context clues. We're given a vocab word. We should probably use it. So, our vocab word that we are given is midpoint. And we're given it twice, but that's okay. We'll use them both at one time. So this is when, if you were doing this on your own, you'd be like, oh, okay, I'm given a vocab word. I'm going to go to this lovely sheet that Mrs. Geyer gave me, and it says, a point is a midpoint if and only if it divides a segment into two congruent segments. So if I give you a midpoint, I then want you to tell me which two segments are congruent. Right? Write a little congruency statement. Now, in this situation, we'll be able to do it twice because we have two midpoints. So it says B is the midpoint of segment AC. So if B is the midpoint here, which two segments can we say are congruent? AB and DC. Yeah, so we would say segment AB is congruent to segment BC. Stephen, you paying attention back there? And we can do the same thing, but on point E, right? So for E, then we can say that segment DE is congruent to segment EF. How could we say that? Well, we were given vocab. So definition of a midpoint. All right. So now we want to prove that segment BC is congruent to EF, right? And we have those two segments, but right now they are not together. They are in different congruency statements. BC is over here, EF is over here. We got to figure out a way to bring them together. Well, if you look at your given, do we know something about AB and DE? They're congruent, right? Yeah, we know that they are congruent. We might even have an extra line in this one. Yeah, it technically, so I did it last year. I did this in two separate steps. But technically, I would say you could go ahead and do this all in one step because you know that AB is congruent to DE, right? So if they're congruent, that means they have equivalent values. So if these are congruent, then BC will have to be congruent to EF. We actually have a bunch of extra lines. We don't need them. Look at us. We're just slashing steps here, left and right. Yeah, because last year I complicated it. I went to congruence and then we substituted and then we went back. You don't really need to. It probably just depends on what like people said, you know? But with these, yeah, if you notice, oh wait, A, B, and D, E are congruent, then yeah, use the transitive property. If these are congruent, then these are congruent, and you're done. So transitive property. Don't need those two. Look at that. Slash and steps.